So this video is going to be, what does I depend on? And when I say I mean I as in rotational inertia. And for some reason, this is sometimes called moment of inertia too. But this is that missing piece, the other thing that impacts the angular acceleration of an object other than torque. So it's kind of analogous to mass when it comes to forces acting on an object, right? Meaning if the rotational inertia of an object changes, then the resulting acceleration from a same torque is also going to change. So today we're going to look at what things impact the rotational inertia and what relationship might they have with the resulting acceleration, so we can try and figure out, what goes in this blank in the rotational inertia equation. So we're going to do that using, of course, our lovely ladybugs again, our ladybug and platform. And what we're going to do is we are going to keep the torque the same because we want to apply the same torque, but we're going to change a couple of these variables here. So we're going to change the mass, platform mass. We're going to change the outer radius and the inner radius. Okay. So the first thing we are going to change is the mass. So I'm just going to create myself a little data table. So I have mass and resulting angular acceleration, and I'm going to keep my net torque nice and constant at 4 Newton meters, right? So that I can actually see how does the mass change that angular acceleration. So right now we have a mass of 0.12 kilograms. So when I hit go, that gives me a platform acceleration of 4.167. So I have a mass 0.12 and an angular acceleration of 4.167, and that's in radians per second squared. Mass is in kilograms. And then remember, when we're trying to figure out the relationship between some things, it's good to like double, half, triple, etc. So first I'm going to double. So I'll change this mass to 0.24, right? And I'm going to make sure this is still at a torque of 4. When I hit go, all right, now I am getting an angular acceleration. So I got 0.24. I got an angular acceleration of 2.083. Now you might be already able to see the relationship that is existing, but we'll do one more piece of data. We'll do half of 0.12. We'll see what we get. So I'm going to do 0.06. And make sure this is 4, and I'm predicting this to be around 8 if the pattern I'm seeing is continuing, and we get an angular acceleration of 8.33. So 0.06, 8.33. Now, like I said, I am seeing a pattern. So what I'm seeing between these first two is that if my mass doubles, so if I get 2m, then that leads me to half the angular acceleration. And between these two, I saw if I half the mass, then I get twice the acceleration. So that tells me that there is an inverse relationship between mass and angular acceleration. So I could either write that as like net torque over mass equals something acceleration, or I could put them on the same side and realize that maybe mass has something to do with whatever is in this blank. So mass times acceleration. Okay. But there might be other things that also impact acceleration, so I'm not going to fill it in completely. So the next thing we're going to look at is the other thing I can change about the platform, and that is the outer radius. So I'm going to have R and alpha, and again I'm going to have a net torque of not 0, 4. Okay. Now, as I change the outer radius, it's going to be really important for me to make sure that this torque remains constant, because as I change the outer radius, where the force is applied is going to change, and that's going to change the torque. So as I change this outer radius, again, I'm going to make sure that I have a nice constant torque of 4. So I'm going to go back to my original mass. Remember, that gave us an angular acceleration of 4.16. So my outer radius initially was 4, and I got 4.16 radians per second squared. Okay, so now I'm going to half the radius to 2, right? See how my torque changed to 2, so I'm going to change this back to 4 to make sure that that's nice and consistent. So since I have a smaller radius, it's applying a bigger force. That's why you just saw that blue arrow increase. So when I hit go, ooh, now my angular acceleration is at 16.6. So 2 meters, 16.6. Okay, and then I'll do one more. I'll do 1 meter, because that'll be a quarter. And, oh, this would probably be very big. I'm going to change that to 4, right? No, my force got even bigger. Ooh, 66. Okay. So 1 meter and 66. Okay. So the pattern that I'm sort of seeing here, and it's not necessarily exact because their numbers are a little bit wonky, but what I'm seeing here is that if I half the radius, I get about 4 times the angular acceleration, because 4 times 4 is 16. And what I'm seeing between these first and last one is that if I quarter the radius, that's leading to about 16 times the acceleration. Because 4 times 16 is about 64, which is about 66. So what this is telling me is that R and angular acceleration have an inverse square relationship. So if I was to write that out, I would say that the angular acceleration is proportional to 1 over r squared. Okay, so if 1 over 1/2 squared, right, that's going to be equal to 1 over 1/4, which is going to be equal to 4, right? 1/2 the acceleration, 4 times the angular acceleration. So I can either write that, nope, not forces, torques, over r squared is m something alpha, or I can put it on the same side, net torque is mr squared, maybe something else, alpha. Okay. All right, and then the last thing that we're going to look at is the inner radius. Inner radius. Now, this one is a little bit weird to kind of conceptualize, because what we're doing when we're changing this inner radius, let me go back to 4 here, and I'm going to keep that at 4. I change. Actually, let me just reset this back to the beginning. Yep. Okay. So when I'm changing, no, stop. When I'm changing the inner radius, what I'm actually doing is I'm kind of hollowing out this platform. Now, one big thing to keep in mind is notice that that platform mass isn't changing. So as my inner radius increases, more and more mass is getting pushed to the outside. Okay? So instead of my mass being like evenly distributed around the solid platform, my mass is getting distributed further and further towards the outside. So that's what we're changing when we're changing the inner radius. So we'll first start it at 0.5. Let's make our life easier. 0.5. So I got my torque of 4, like I have been using the whole time. Outer radius of 4, inner radius of 0.5, right? So our initial, if we had no inner radius, was 4.167. So now I'll hit go. All right, I got 3.98. So radius of 0.5 meters, alpha 3.98. Hey. And I can continue, right? Let's do double that, 1 meter. Right. Still got a torque of 4, perfect. Go. Now I got 3.765. 1 meter, 3.765. Okay, so not as clear of a pattern as I was seeing before. So let's do 2 meters, so that'll be 4 times. All right, got a torque of 4. Still, go. All right, now I'm at 3.2. 2 meters, 3.2, and we'll do 4 meters. So all of my mass is completely on the outside. Making sure I have a torque of 4. And now I'm at 2 radians. Okay. So this one isn't as easy of a pattern to see as the other. In fact, I can't really see any pattern. So that tells me that the inner radius definitely affects the angular acceleration, right? Like it's definitely changing, but it's not as clear of a relationship as we might expect. So that suggests that maybe there's like a subtraction involved or something like that. But I do see that it is some form of an inverse relationship in the sense that when that R increases or as the mass gets pushed towards the outside, alpha is decreasing. Okay? So basically what I'm seeing is that whatever was in that blank, in that net torque statement, right, it has to be based off of M, the outer radius squared, and something to do with the inner radius. Okay, so it depends on all 3. Okay, and we can kind of define this as like how much mass and where the mass is located. And the variable that kind of describes this is the rotational inertia, which is represented with the letter I. Okay, now I is technically calculated by using a summation of all the masses where they are squared. So that's where we get that mr squared from. Now this would be like literally each individual atom. So this summation can be infinitely long, okay, and usually use the calculus to solve. We're not going to do that. I'm going to give you common rotational inertias. Okay? But what we need to recognize is that if I increases, what that means is that the mass is greater or distributed further from the axis of rotation, meaning it's towards the outside. And that's going to lead to less angular acceleration with the same torque. Okay. If the rotational inertia is less, that means the mass is smaller or distributed closer. That's the F. It totally got cut off. But if I decreases, that means the mass is smaller or distributed closer to the axis of rotation. So some examples is, let's say I have this massless rod and I want this thing to rotate as slow as possible. And I'm applying the same torque to it. So what I want is I want to have a really, really big mass as far from the axis of rotation as possible, because that's going to give me a really, really big I. And if I apply the same torque, I'm going to have very small angular acceleration. Now, let's think I want to make this thing whip around as fast as possible. So what I'm going to do is I'm going to put a very little mass very close to the axis of rotation, possibly even on it. And that'll make me have a very, very large angular acceleration, as this I is going to be very small. We're going to do some demos in class that are going to kind of solidify this for us. So that brings us to our grand total net torque equation. So this is known as Newton's second law for rotation, and it's the idea that the net torque, so all those forces at distances from axis of rotation, is equal to the rotational inertia, basically where the mass is located, times alpha. We call it the Newton's second law for rotation because it looks pretty similar to Newton's second law. Net force equals ma, right? Net force and net torque are analogous, mass and I are analogous, and alpha and A are analogous, just for one's for linear, one's for rotation. Okay, so one thing that we're gonna do before we end this is I pose a question to you. Let's say that I have a solid and a hollow object with the same mass, same radius, and same torque going down a hill. So this is like a hollow cylinder, we could call it a hoop of mass m, radius r, and then this is a nice solid cylinder or disc of mass m and radius r, and I'm sending them down an incline, and I want to know which one lands first. They have the same torque. So I have this simulation from O Physics, which is a great place to go. Okay. We could have shown a frictionless cube if I wanted, and some solid spheres and spherical shells. Okay, these I values are, somebody went through and did the calculus of all the sums of all the masses at all the infinite radiuses. These are the values I'm going to give you guys on your reference table. But for now, we're just going to look at the solid cylinder and spherical cell. So have your prediction, which one gets to the bottom first. And I'm going to hit run. Whoa! So the solid cylinder gets to the bottom first because both of these experience the same torque, but the solid cylinder has less I. In fact, it has half the I as the spherical shell, which means that the solid cylinder is able to accelerate rotationally faster down the incline. Because it's faster acceleration down the incline angularly, it's going to rotate faster, roll faster down the incline, so it's going to get to the bottom of the incline first. We'll come back to this a lot as we go through this unit, but I just wanted to put it to you first. Okay. So big ideas, we have net force as I alpha. I is how much mass and where it is located, and that's our rotational inertia. That's the end.